and I talked about the open FRW universe that results from the decay of a positive cosmological constant to a smaller cosmological constant. And a bit about the phenomenology of it. That was all. Let's see what I talked about. Well, I talked a little bit about the holographic principle, but that has nothing to do with the rest of the talk. Then I talked mostly about the decay of metastable de Sitter space into flat space, and what the cosmology of it is. Some of the anthropic bounds on negative curvature that result.
Explain how the function went into entropy.
What's that?
Explain how the function went into entropy.
No, because I don't know. But we talk more at a phenomenological level. So I guess I'll begin. What I want to talk about today is a holographic framework for eternal inflation. In my mind, two of the really, really central questions of physics and cosmology are eternal inflation on the one hand, and string theory. I don't know what to call the combination of ideas that came out of string theory, black hole physics, quantum gravity, entropy, all of those sets of questions. The connection between cosmology, in particular eternally inflated cosmology, and the more theoretical or mathematical things that have emerged out of the last 20 years, 15 years of studying, let's say, non-perturbative string theory. There seems to be almost no connection. There's been very, very little literature by string theorists on inflation, almost none. What does exist, the little that does exist, is usually of the form, oh, take this particular setup, KKLT, or whatever the right acronym is, and look how to modify it to find some potential which looks sort of like what inflation requires. And then to say either we found it or we didn't find it. But very, very little in the way of principle, in the way of trying to understand a set of principles which would allow us to bring the power of the mathematical technology that's been developed and use it to understand cosmology. Almost nothing. If anybody knows any counterexamples, please tell me. The framework for thinking about cosmology that I think is all but inevitable, and that we're not going to escape from, is a framework based on a landscape of many, many vacua, each one of which has its own cosmological constant, perhaps an extremely dense, what Joe Polchinski and Raphael Busso called a discretium of vacuums, so dense that they're likely to be just about anything you can look for. Seems to me that's the way things are going. Combine it with what we know about inflation and what we know about inflationary cosmology, and a picture emerges. The picture that emerges seems to me all but inevitable. It's the picture of a universe that starts with very, very high energy density somehow. We don't know how it got there. None of this is intended to be a first principles explanation of how the world got here. I have no idea how this world got here. But at some point in our history, it seems likely that the energy density of at least some portion of the universe that eventually evolved into our corner of the universe was very high. High anyway on the scale of ordinary energy densities. Very likely got trapped at a local minimum in which it inflated, perhaps inflated for a long time, many deep foldings. This has nothing to do with the standard slow roll inflation. It was eternal inflation. And the only way out of that eternal inflation was from the fact that there are many vacua with a large number of vacuum energies. This is a cartoon, of course, of a complicated landscape, and perhaps some series of bubble nucleations and tunneling events cascaded down to some low energy vacuum that we live in. I don't know any other framework that I think is robust and that would sit well with the various things we know, including the existence of a small, unexplained cosmological constant, including the success of inflation, and including the knowledge that we gained from string theory.
And what are you tunneling through from the field gravitational configuration to field gravitational configuration?
Yeah.
Complexes to complexes.
Yeah. And I discussed a little bit the difference between a parallel view and a series view of this kind of cosmology. Let me just remind you. Well, let's imagine a global look at the entire universe. Now, yeah.
Is there any significance to the route that you take as you go from one vacuum to another? And is there any observable?
I would guess all possible routes that are possible happened in an eternally inflating universe. So no, I don't think there's anything special about any particular route. But I think a more accurate picture of what eternal inflation is supposed to be by its advocates, by the advocates of the idea. And a more accurate picture is to say, well, somewhere in the past we started with some vacuum down low on the blackboard with some relatively large vacuum energy. Let's put that point up here, if that point was stable, if it really was a stable vacuum with no way out of it, to tunnel out of it, then we would live in de Sitter space, or the world would be de Sitter space, perhaps a small fluctuation away from de Sitter space. And this de Sitter space is roughly just the lower half blackboard here. That's a conformal picture of de Sitter space. But then, if decays can take place, they cannot take place everywhere simultaneously. That would violate causality. And so the natural expectation is that you're dealing with something like a metastable phase of a metastable system, and bubbles nucleate. All right, the simple bubble nucleation would consist of a region of lower cosmological constant. If we tunneled through to some lower cosmological constant and just sat there, then in here, again, we would have de Sitter space with a smaller lambda. But again, the picture would be the same. It would terminate in the same way, same sort of space-like end to infinity, time infinity. But one can also have a series of such tunneling events. We can have a series of such tunneling events, which means that as we follow a path, we could follow a path through a series of vacuums. That would be the series point of view. But at the same time, much of this may be going on in parallel.
In what space and what time?
Vertical is time, as always. Horizontal is space.
And so you talk about tunneling and the blue path going backwards in time.
Who's going backwards in time?
Its time is going which way? That time went up.
No.
But in your conversation, you were talking about the other way. You said you could.
Oh!
How does that diagram and that diagram work?
Yeah, good. Okay. So here's A, here's A. Here may be B,
Yeah.
this may be B, But there also may be a route down here that takes you to C. So this might be C. All right, but then B to get K to D. So D might be here. Okay. So one thinks about from one point of view, if you were a world line, I don't want to use the word observer, I have no idea what an observer is. Just like draw a world line in here that goes from the bottom to the top. That world line will pass through a series of vacuums according to this picture. If it ever gets down to zero cosmological constant, and there's no reason why it shouldn't, we know that there are vacuums with zero cosmological constant. They're the supersymmetric vacuums. I don't believe, frankly, that there are any others. And certainly nobody has ever given any reason why there would be a vacuum which was not supersymmetric with exactly zero cosmological constant. There can also be negative cosmological constants. But if you end up somewhere with zero cosmological constant, the picture has to connect together with a flat space vacuum at the end of time. A flat space vacuum from the point of view of a conformal diagram just looks like a diamond. And what this region is up here is it's a sewing together or a pasting together of a region which is approximately flat space and which ends up in a flat space cosmology. Flat space means vanishing cosmological constant, sewn together with a region of the Sitter space. All right, so that's a cosmology. And of course, this is a very multi-dimensional space. From any point, you may be able to tunnel in different directions. And the result is going to be a branching system of vacuums which conceivably could fill up every point on this landscape. Now, is there an alternative to this? I don't know. I don't know an alternative to it. I know my friends who believe in inflation, Alan Guth, Andre Linde, don't see any way to avoid this kind of picture. There are other people who have other views, but I don't understand.
When you talk about tunneling, this means that there's a kind of a local minimum, and this means that you envisage a kind of a homogeneous patch, which is describable in a macroscopic way by a cosmological constant, and a local expansion, and then it tunnels into another.
Yes.
Why do you talk about tunneling? Why can't you just have microscopic chaos everywhere? All kinds of mess.
Because microscopic,
What makes you do the tunneling?
we can have microscopic chaos, but if some little region of space gets trapped in a region like this, it's going to inflate. And when it inflates, it'll stretch itself out and become...
I'm all for that, but I don't see why you have to go into the tunneling baroque business.
Tunneling is not something that's up to you. Tunneling is not your choice. It's not baroque. It's inevitable. If you get trapped in a vacuum like this, and there's a lower vacuum there, you're going to tunnel.
Yeah.
You don't have a choice.
Yeah, if there is, yeah.
Yeah. Okay, so what we think we know, or what string theorists, or various string theorists, seem to have found, is a very, very, very rich landscape of vacuums. They all seem to be connected. They seem to be on the same configuration space. They seem to be on the same configuration space, and there seems to be no obstruction. Now, this is something that may or may not turn out to be true. If it doesn't turn out to be true, then we forget the story. At the moment, it looks mathematically fairly robust, but not rigorous. That such a complicated landscape of vacuums exists. But if it does, I cannot think of any way around this particular picture. Therefore, it has to be tracked down. There is no alternative to working out the consequences of this, but even more than the consequences of it, working out what it really means. Because at the moment, it's just a picture that's been concocted by cosmologists. In fact, the picture was not concocted by cosmologists. They draw another picture, this picture was concocted by me, namely this literal picture, as a picture. But the basic idea was concocted by Alan Guth, Andre Linde, Alex Valenkin, and other cosmologists. Paul Steinhardt was one of the first people to think about this. The new ingredient that came from string theory was the existence of many, many vacuums. All right, now I'm not here to sell you many, many vacuums. I'm here to ask the question, what is the basic mathematical framework for probing this system? And in my view, the basic mathematical framework has to be looking backward from some point in the future and asking about everything that's in the backward light column. The reason I think that's the natural framework, as opposed to a picture in which you cut through everything and think of a sequence. We're talking about how do you do quantum mechanics in this context. All right? Cutting through everything, cutting across horizons. Incidentally, these geometries have horizons. Anything out here cannot communicate to anything inside here. So there are event horizons. And we have learned the dangers of cutting across horizons and trying to think globally. We've learned the dangers of that in thinking about black holes. So one view of it is to say, let's stay in our home patch and try to formulate a set of principles that govern everything that can be seen from our own vantage point up in here, everything else outside being kind of a mathematical fiction or redundancy. But I think there's 2 points of view. What I'm going to talk about is detailed mathematical proposal. The detailed mathematical proposal for discussing what goes on up in here. There are 2 viewpoints that you can take. The first is a sort of phenomenological viewpoint that we actually live in a place like this, and to try to understand the mathematics of what we see in our own universe. Of course, this can't be exactly right. We seem to live in a world that has its own cosmological constant, and so we don't seem to be at a terminal point at which the cosmological constant is settled down into zero. Incidentally, you don't tunnel out of a vacuum that has zero cosmological constant. If you really get to zero cosmological constant, you're stuck at it. You don't tunnel out of it. There's no excess energy around to nucleate bubbles. And in particular, if it's a supersymmetric vacuum, you won't tunnel to a negative cosmological constant. So these are sometimes called terminal vacuums, endpoints. And in this picture, the entire world is this very complicated fractal of structure, but we want to concentrate on what one terminal vacuum sees when it looks back. As I said, one viewpoint is a phenomenological viewpoint that we live in such a world. We don't. We live in a world with a cosmological constant, and so at best this can be an approximation. The other viewpoint, which frankly I'm more interested in, is using or studying these kind of transitions, studying the transitions from positive cosmological constant to zero cosmological constant as a way of classifying, defining, and probing the landscape. In other words, as a way of trying to give a definition, a quantum definition to the cosmology, to this cosmology. And that's what I'm much more interested in. A classification, for example, a classification scheme for classifying not only the metastable vacuums, but the various kinds of transitions that can happen. What I'm going to tell you is I think that the classification scheme is in many respects very similar to the classification scheme of anti-de Sitter space. This has not been worked out in any great detail. The anti-de Sitter space, of course, is not completely worked out, but the holographic view of the anti-de Sitter space puts anti-de Sitter space vacuums in one-to-one correspondence with conformal field theories. Minkowski signature conformal field theories. So that's a belief which I share that, that anti-de Sitter space cosmology, and that means eternal, unchanging anti-de Sitter space, is described by a holographic description involving conformal field theories. And what I'd really like to do is to put as much rigor, or at least as much conceptual rigor, into real cosmology. Real cosmology now I'm taking to mean this kind of eternal inflation. So my lecture today is not going to be about phenomenology. It's going to be about the proposal for basically using conformal field theory to study what goes on here. But not only to study, but to define these transitions, to give a mathematical definition of them, and to do for eternal inflation what conformal field theory does for anti-de Sitter space. Okay, so let me just remind you quickly what one of these bubbles looks like from the inside. The Sitter space decays, and let's say it decays into a vacuum with vanishing cosmological constant. Then the picture is an open FRW universe. FRW, Friedman, Robertson, Walker, with space-like surfaces which look like this. That's what one sees inside this bubble. The space-like surfaces are infinite because the metric diverges at these points. This is a conformal diagram. It doesn't represent actual distances. And so this patch is an open FRW infinite universe with vanishing cosmological constant, so it ends off in flat space. That's the basic thing that I want to study. A transition from de Sitter space to FRW open infinite evolving bubble. All right, the mathematics for this, as far as it's known, is the Coleman-De Luccia instanton, called the CDL instanton. The CDL instanton plays the role of the instanton, the Euclidean instanton, which determines the rate and the properties of what's seen in here, the rate per unit time, space-time, and so forth, are actually decaying. So I'm going to begin with a review of Coleman-De Luccia instantons. Even before that, let's just talk about de Sitter space itself. Let's talk about infinite eternal de Sitter space as it would be if we were just sitting up here in one of these vacuums forever and ever and ever. What does de Sitter space look like? Let me first begin with Euclidean de Sitter space. Euclidean de Sitter space is the analytic continuation of time to I times time, and de Sitter space is just a sphere. If we're in 4 dimensions, which I'll take us to live in 4 dimensions, then this is a 4-sphere. A 4-dimensional sphere, it has a symmetry SO5. Why do I say SO5? O5. A 4-sphere has symmetry O5, rotating 4 spheres and so forth. We can slice that sphere right through the middle here and think of that as kind of initial conditions. For the moment, I'm imagining time flowing upward. Usually you have time flowing upward, but later on we're going to see some reasons for making time flow horizontal, at least part of the time. But right now, time flows upward, Euclidean time. There's no unique sense of time on this Euclidean sphere, but if I slice it and foliate it horizontally, that gives me a sense of time. Okay. And let's call this point over here and this point over here, let's call that B and A. Just arbitrary points with an arbitrary circle here. All right, how do you analytically continue this to Minkowski space? You analytically continue the sphere to a hyperboloid. T goes to IT, the sphere becomes a hyperboloid, like so. So this is Minkowski space, de Sitter space, but the initial surface at t equals 0 is exactly the same. Since t equals 0 and it equals 0 say the same thing. The surface t equals 0 is the same as the surface it equals 0. And so there's a correspondence, an exact correspondence, between this initial circle here and the initial condition, or the, let's call it the throat or the neck of de Sitter space. Okay, this point over here would map to this point, and this point would map to this point. And that's de Sitter space. In a nutshell, that's all of de Sitter space. Okay, now I want to take that de Sitter space and draw a conformal diagram of it. Incidentally, I'll draw my pictures in 2 dimensions. You do have to think in higher dimensions, but I'm going to draw all my pictures in 2 dimensions.
You do get the same picture if you do T-duality along this direction.
What's that?
You'll get the same picture if you do T-duality along this
Along which direction?
the arbitrary circle.
Do T-duality along here.
Then,
Okay.
Is this a coincidence?
I don't know. No idea. Right now, I'm just doing the Minkowski continuation of a simple Euclidean geometry, perhaps. I don't believe it does. Anyway, this is what real de Sitter space looks like. It's a hyperboloid with an exponentially increasing scale factor. To write the, I don't need to write the metric for it. You all know the metric for it. And now, if I want to make a conformal diagram out of it, what I do is I slice it right down here. I'm going to slice it and open it up. Okay? Think of it as having the topology of a cylinder. I'll slice it and open it up on the blackboard for you. And if I do so, it looks approximately like this. Or, first of all, I will slice it, open it up, and then express what I'm left with in conformal coordinates. Conformal coordinates, meaning that light rays move at 45-degree angle. This is it. It's opened up. The place that I sliced it right down the middle and opened it up, these are these edges over here. Okay. Around the back over here, that's this vertical line here. T equals infinity is up here, and t equals minus infinity is down here. A true Penrose diagram would only have half of this. It would only represent, well, this is a doubling of the true Penrose diagram of it. But it's helpful to think of opening the whole thing up and spreading it out on the blackboard like this. Okay, that's de Sitter space. Now let's plot these points. Let me put B right in the middle. B is right in the middle, but a point in Euclidean space becomes a light cone in Minkowski space. Oh, incidentally, these are perfect squares. The 2 halves are perfect squares. Okay, so let's take this point here and remember that B really becomes a light cone. All right, if we now extrapolate the light cone, it will go up to this point, halfway here, halfway here, halfway here, and halfway here. Suppose I do the same thing, let's see, that was B. I do the same thing at A. A is over here. There's 2 images of A because I've opened up the sheet. All right. And the light cone at A is like this. So this is a picture of de Sitter space. I've just marked some points, A and B, drawn some light cones. You can take one of these diamonds here, and one of these diamonds is called the causal patch. It's called the causal patch. It has horizons, future horizons, past horizons, and a standard bifurcate, 2 bifurcate horizons, ordinary polar coordinate singularities over here and here. That's de Sitter space. The metric on it blows up exponentially, well, it blows up as you go up to the top of the diagram and as you go down to the bottom of the diagram. Now, what I want to come to now is not de Sitter space, but the decay of de Sitter space, the decay of de Sitter space to a flat vacuum. So let's consider that. Here's what we want to think about. Vanishing cosmological constant over here. Now we start in A over here, somewhere in the vicinity of this minimum, not right at the minimum. We'll see why in a little while. And then we're going to decay or tunnel through to a second point B over here. The pure de Sitter space would correspond to just sitting in the vacuum here without any disturbance. Now we're thinking about an instanton which makes a transition from A to B. You might think of this as a time flow from A to B, but I'm going to draw it in my own way, the way which will become clear as we do it. We're going to look for a Euclidean solution of the equations of motion of gravity together with the scalar field, which begins over here with the field being A. The field flows from here to here until it gets down to the other side over here where it's B. So the Euclidean geometry is some deformed sphere. It's not as symmetric as it was before. And it starts here at A and travels across to here where it's B. I'm going to call the horizontal, well, not the horizontal direction, but kind of the radial direction away from the point A. I'm going to call that time, T. Now, I'm now making an exception to my usual rule of plotting time upward. But that's Euclidean time. Keep in mind it's Euclidean time. This instanton satisfies some equations of motion. Well, before I say what the equations of motion are, the field simply flows homogeneously. Homogeneously means it doesn't depend on angle here. The field on each one of these circular slices here is homogeneous, but it flows along the time direction from A to B. The symmetry is less than the symmetry of the original sphere. It's SO or O4 instead of O5. Okay, we've broken the full symmetry of the four sphere, but it still has a kind of azimuthal symmetry around the axis through A and B. And that's O4 symmetry, one down from O5. Okay, and the orbits of the O4 symmetry, if I were really to draw them, of course, would be more complicated. But if I map them onto this two-dimensional figure, they're just the symmetries which travel along these surfaces of constant time, the isometries of the constant time surface. That's O4 symmetry. The metric of this is just ds squared is equal to dt squared plus a of t squared times d omega 3 squared. Omega 3 squared stands for a three-sphere, and it's these circles, these things that I've drawn as circles, which are really the three spheres. Okay? A of t starts at 0, expands, and comes back down and collapses at B. So the time runs from something finite, 0 at this end, to something finite. Time here would be proper distance along this surface. And it would run from t equals 0 to some maximum t naught that's determined by the actual solution of the instanton. Okay, I need to write down the equations of motion. The equations of motion are very simple. They're FRW equations, except continued to imaginary time. A dot over A squared equals phi dot squared minus V of phi plus 1 over A squared. This is the curvature term. This is the potential energy. The reason for the negative sign instead of a positive sign is because I've continued to t equals it. Okay? T equals it changes the sign of the two terms with dt squared in them. And this is the equation of motion for the field to go from here to here. The field is also flowing from here to here. Keep both pictures in mind. The field, as you go from one pole to the other pole, is traveling over this hump and settling down somewhere at B. Next fact, what about the equation of motion for phi? The equation of motion for phi is phi double dot, just a scalar wave equation. We're only phi double dot plus 3 a dot over a times phi dot plus v prime of phi is plus
Should there be an I then? Oh no,
there's two of them. I think I may have this. Yeah.
And that's been extra minus just compared to the usual one.
Yeah, I think maybe there's a minus sign here. Equals. Yeah, I think there's a minus sign here. Not important. Equals 0. Okay, so these are our equations of motion. Main point is they're coupled equations of motion, which couples A to phi, and there are solutions which take you from here to here in a finite amount of time on a finite deformed sphere, and the deformed sphere has O4 symmetry, a lower symmetry than the original symmetry of the sphere itself. Other facts about this: if you look, the geometry is completely smooth at these poles. That means as you move away from the pole here, it's just polar coordinates, and it's quite clear that the scale factor just increases linearly with time as you move away from this point. That's just scale factor of a point with a series of spheres around it. The radius of the sphere just increases linearly with proper distance away from the point. And so the boundary conditions are at this point, A dot is 1.
And then you get there's an A which is a scale factor. And
A is a scale factor. Oh, I'm sorry. Very good. Very good. Very good. A here is not the scale factor. A is just a point.
Related to phi somehow. The fact that you're off center means that you have some phi dot not equal to 0 there.
Yeah. Yeah, I'm going to call this capital A and capital B. That's what we're talking about. All right. Yeah. Capital A and capital B, this A is a scale factor. But as you move away from point A, the scale factor increases linearly, like time itself.
What I'm trying to figure out is the point, capital A, which is now off center.
Yeah.
That clearly is related to phi dot. If you would be phi dot is equal to 0, then you're stuck in the zero space.
No.
There must be a relation between being off center.
No.
And that's what I'm trying to figure out.
No. You start here and you end here, with phi dot being 0 at both ends. Now, there's several ways of understanding this. First of all, if you actually were sitting here, your field would sit there forever and ever.
Phi dot would be 0.
Phi dot, no. Well, if you were there at rest,
Yeah.
phi dot would be 0, you just sit there forever and ever. If you're over here with phi dot equals 0, you don't sit there forever and ever.
Right.
Okay. In fact, in order to understand this, what you really ought to do is, with regard to Euclidean equations, we should turn the figure upside down. Turning the figure upside down turns it back into a Newtonian mechanics problem. All you have to do is change the sign of the potential. What you're doing is you're starting over here, at rest, rolling down to here, and then rolling up to some point where you come to rest again. That's the start at rest, roll down to here, and roll back up to here. And you've got to choose these points in just the right way that it all fits onto a closed sphere. You don't have an
Do you have any idea dynamically why you get pushed off center?
Yeah, of course. That's the thermal energy in the de Sitter space. The thermal energy in the de Sitter space.
It's a fluctuation.
Yeah.
Oh, okay.
Yeah, it's thermal energy in the
I
de
like
Sitter
that.
space. Yeah.
Now,
But we'll also see it another way. We'll also see it another way.
you could get pushed off thermally off the other side also, couldn't you?
Well, here's cosmological constant
I think you
0.
have your capital A,
Yeah.
if you have the thermal energy,
Yeah.
and then you can go to the left.
Oh,
And then
and there's something to the left, sure.
And then you go somewhere else.
And then you go somewhere else. That's why I say that this is a branching, complicated mess. Okay, so this is our, and the other, A dot is equal to 1 at A, and it's equal to minus 1 at B. So it's either 1 or minus 1. As you move away from A, you're expanding. As you move toward B, you're contracting. Of course, it's really not asymmetric in that sense. It's just a definition of the flow of time. The other boundary condition is that phi dot equals 0 at both ends, and that's just smoothness of phi at the polar coordinate singularity. Phi requires that phi dot be 0 at the two poles. Now what I want to do is I want to...
And to say that again, is phi not very important? Phi. Is that phi the same as your field?
Yeah.
And you have not the quantum field phi, well, the matter field phi.
Yes.
Into
It's phi. It's a phi. It's what it
into
is.
an angle.
Or whatever you call it. No. Where's an angle?
The same, the phi dot.
It's the same phi. It's the phi that's here.
And why is it necessarily equal to 0? The phi dot?
Because the smoothness on the sphere, this is a polar coordinate singularity here. Okay? The symmetry of the problem tells you that phi doesn't depend on angle. Right? A smooth field at a point which doesn't depend on angle has to have phi dot equals 0, if by that you mean the radial derivative of the field. Okay? So it's just the smoothness of a field at a polar coordinate point, where the field doesn't depend on angle. Okay? So
that's very important that it be in the vicinity of the local maximum on that.
yeah, otherwise it wouldn't be a solution. I mean, whether or not there is a solution depends on the potential. So for a potential which looks roughly like this, there's usually a solution. The solution can fail. There are situations where you don't find solutions. But when you do find a solution, it's called the Coleman-De Luccia instanton. All right, and as I said, it has symmetry 04, which is a lower symmetry than the original symmetry of the de Sitter space. All right, now what I want to do is I want to continue this to Minkowski space, to Minkowski signature. So I'll show you what it looks like. Those who've gone through these sort of exercises before can sort of figure it out by inspection. And I'm going to do sort of mostly just inspection, but I'll show you what the answer looks like, and then we can come back and roughly understand it. Okay. Again, let's start with point B right at the center. Okay? But now, point B is exactly as it was over here. It's a light cone rather than a point. So again, we have exactly the same thing as before. Essentially no difference to what we had before. Point A is out here. This is point B. And in fact, it looks exactly the same. The light cone and these two branches over here. But that's not the end of the geometry. The geometry has to be continued into these regions and into these regions. Okay, let's continue it from point A. Point A, this is capital A, not small a. Starting at point A, and running the field equations, not Euclidean, but Minkowskian, starting with 0 velocity for the field, what happens? It falls down to here. It falls down to here and comes to rest. Why does it come to rest? It's cosmic friction which makes it come to rest. But starting over here, it just sinks down to the de Sitter point. So starting over here and going up in time, real time now, not imaginary time, you will eventually get to the minimum over here and come to rest. The rest of the diagram looks like this. The same is true if you work backward in time. This whole thing is time reversal invariant. If you found yourself over here at rest, you must have come from here. So going in forward and backward in time, from this point where you are at rest here, you simply sink down to the minimum. This region up here looks exactly like de Sitter space. The whole thing differs a little from de Sitter space because you went from A to the minimum, but at late times, it looks exactly the same as the de Sitter space up here. Okay. That's the de Sitter half of things. But what happens from B? B is over here. So let's go forward in time from B. What does the field do? Well, it falls down to the bottom. What's at the bottom? The bottom is zero cosmological constant. Therefore, you'll have to end up in flat space.
Oh.
Okay, question? You have a question? Go ahead.
It's nice.
It's what?
It's nice.
It's nice. Yeah, that's a nice picture. All right. This is the Minkowski continuation of the Coleman-De Luccia instanton. What about domain walls? The domain wall is the place where you make the transition right over the top of the barrier here. That might look something like this. It would be in here somewhere. It's not a terribly important concept for me. Somewhere in here would be the domain wall.
Can you make another picture, not in this language, but going back to the original, the global de Sitter space, draw a global patch, draw a patch, draw a static patch with the horizon, which is the universal.
No, that's the solid
And
here. That's the solid here.
And then show how
And here,
that,
see, what happened here?
how that staticity breaks up, and you go to a new staticity, and you have a temperature, and that static patch, and then that breaks up.
Oh, if you went from one de Sitter to another?
Yeah, I like what you're doing here.
But you mean supposing you go to another de Sitter instead of zero cosmological constant? Is that what you're
And
saying?
then you go to another patch, you go to another patch with a new temperature.
Well, yeah. Yeah. And that would look, I'll tell you what it would look like. If this cosmological constant in here were very small, non-zero but small, it would almost look exactly like this, but instead of having this flat space here, you'd have another space-like boundary like that.
Mhm.
Yeah. But I want to stick with flat space, partly for simplicity and partly because I don't, I say for simplicity, but that suggests that maybe I know how to
You
think
know,
about
what I
it.
have in mind is, of course, in the reheating, when the de Sitter thing starts to break up, and
Well, where would
and you lose
yeah, but I mean, let's not confuse this tunneling here with reheating or with phenomenological inflation. Phenomenological inflation, if it were to occur, would occur in here. Would occur actually after you tunnel through, and would occur in here somewhere. But I don't want to focus on that now. I focused on that last time, that phenomenological inflation would take place in our patch, and would look something like that. But let's not get into that now. That's a separate talk. Okay, now what about this O4 symmetry? The O4 symmetry doesn't stay O4, it becomes O31. In other words, when T goes to IT, the four-dimensional rotation group becomes O31. How does O31 act? How does O31 act? Well, remember what O4 did. O4 was basically the symmetry that took you along these slices. If you come over to this picture, there are 5 or somehow how many different regions. There's a whole bunch of different regions. And the O4 in some of the regions pushes you in space-like directions, not the O4, but the O31. In some of the regions, the orbits of the symmetry are space-like. In other regions, they have time-like directions. So let me show you roughly how the in a two-dimensional world, the corresponding symmetry would work. In these patches here, this is the FRW. This is the FRW patch here, which if you foliate it or slice it by space-like surfaces, each space-like surface is a hyperbolic plane. Each space-like surface is a Euclidean anti-de Sitter space. Okay. And the O31 acts as spatial isometries along the space-like directions. Remember last time, if you were here, I showed you this picture of what the hyperbolic plane looks like. It's a disk, and it has large things in the center, and they get smaller and smaller as you go out to the outside. And if you like Escher drawings, look up limit circle number 4. That's a famous drawing of the hyperbolic plane. That's what the space-like surfaces look like, and they are equivalent to Euclidean anti-de Sitter space. Okay. The O31 is simply the group that moves you around, a group of spatial translations on the space-like hypersurfaces. Any questions? In this region over here, the O31 acts as it orbits partly in time-like directions. And in these de Sitter regions, again, it's space-like. But the important point here is we're going to focus on this region. We'll focus on this region. And so the O31 is just the spatial symmetry, spatial translation symmetry of the hyperbolic geometry of space. So that's the Coleman-De Luccia instanton. Let me write down the metric in here. It's just the S squared equals minus dt squared plus A of t squared times d, and I'm going to call it script h3 squared. This was d omega 3 squared. That corresponded to a 3-sphere. This corresponds to 3-dimensional hyperbolic plane. So it's the hyperbolic analog of the 3-sphere. And here's the dh3 squared. It's the r squared. R is proper distance from the center plus sinh r squared d omega 2 squared. The omega 2 is the sphere of the sky, if you like. You look out, see the sky around you. Omega 2 is the sphere of the sky. R is distance away from you at the center. So this line could be r equals 0. And this is the hyperbolic plane. Every space-like slice has exactly the same geometry except for the scale factor 8. Okay, now, O31 has another life of its own with another geometric significance. It's the conformal group on a 2-sphere. This same symmetry, which moves you around in the bulk, also has an action on the boundary. So let me show you. The boundary is this region here. The boundary of space means space-like infinity. In this picture, it's over here. I'm going to call it sigma. It's also over here. But I'm going to draw you another picture of it, a sort of solid version of it, not two-dimensional, so you can see what it looks like. Okay, here, let's focus on this region over here, all of this region over here. First of all, this time-like infinity of the de Sitter space, before we wrote the symmetry. That's a plane. Actually, it's a 3-space, not a 2-space. Now, down in the lower plane someplace, the bubble nucleates. Here the bubble is nucleating. That's the nucleation of the bubble. It's down here. And it nucleates and spreads out. It smashes into time like infinity, where it's actually infinitely big because the metric is blown up here. But in a causal picture, it just looks like this. That's where the bubble intersects the boundary of the Sitter space. And then there's a cone attached to the top of this, with t equals infinity out here. Here's light like infinity, light plus. And that's the picture of the FRW region and how it's embedded in the Sitter space. The Sitter space down here, nothing up here, but the top of this cone up here is where the FRW region is. Okay. Sigma, the boundary, the space-like boundary of infinity, is this here. Sigma, 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 sigma. It's a two-sphere. I've drawn it as a one circle, but I've lost the dimension in all of this. Sigma is a two-sphere, and the isometries, the 031 isometries, which move you around in the bubble, also have an action on the boundary here, takes boundary points to boundary points, and it acts as the conformal group on the boundary. Okay, that should ring a bell. Conformal group acting on the boundary of the geometry, which is isomorphic to Euclidean anti-de Sitter space. Okay. It suggests that there might be some kind of conformal field theory living on this boundary that describes everything going on in the interior of it. I can't prove that, but we can do some tests of the idea. I'm waiting on this. All right. Time always goes faster than it's supposed to. So I'm getting late and...
Let's do a conformal transformation.
What's that? Yeah, we'll do a conformal trans. I can talk faster and faster and faster and faster and faster and faster and faster. But that's not very good. Okay. There are some tests we can do to try to find out whether the bulk geometry really is described in some sense by a conformal field theory living on the boundary. I don't know what the conformal field theory would be. My guess is that the landscape is so rich, and there are so many such transitions that are possible, that I'm almost willing to bet that any conformal field theory will find a home in this framework. But I don't know that that's true. All right, how do you test whether there might be a conformal field theory living on the boundary? How did they do it when they were studying ADS, anti-de Sitter space? Oh, incidentally, there is a puzzle here. This boundary is two-dimensional. We have 4 dimensions of space-time. In anti-de Sitter space, this could be Euclidean anti-de Sitter space, the dimension, the depth dimension, the dimension into the interior is understood in terms of a conformal field theory on the boundary. Let's just draw on the boundary. Here's the boundary. Here's the boundary sphere. Now this is supposed to be Euclidean anti-de Sitter space. Depth into the interior of the anti-de Sitter space is in one-to-one correspondence with size scale on the boundary. Big things on the boundary are identified as things near the center. Small things near the boundary are identified as things near the boundary. So the extra dimension that appears in anti-de Sitter space, when you think of it holographically, can either be thought of as depth into the interior of the 5th dimension, or a 5th, or whatever the extra dimension is, or it can be thought of as size scale in the boundary field theory. If there is a boundary field theory here, then it's quite natural to suppose that size scale on this boundary field theory, size scale, maps in some way into depth into the interior. Fine. But what about time? Where does time come from? We're missing 2 dimensions, not 1 dimension. So I'll try to get to that. I'll try to go fast. What's the test of whether there is a conformal field theory on a boundary such as anti-de Sitter space, the anti-de Sitter space boundary? The basic test is the existence of an energy momentum tensor. We know that there are correlations. Supposing we have some field theory in the interior of anti-de Sitter space, and we calculate boundary correlators. Do those boundary correlators add up to anything that we could call a boundary quantum field theory? Well, probably the most important test is to test whether there's an energy momentum tensor and whether that energy momentum tensor has the proper properties of the right operator product expansion and so forth. So here would be the kind of test. This is not the kind of test I would like to do. This is the kind of test we did do. I should say who we is, incidentally. This was worked out by Ben Freivogel, Yasuhiro Sekino, Chen Ping Ye, YPH, and myself. We worked out the details of the correlation functions, and I'll tell you what correlation functions are in a moment, the correlation functions that live on the boundary of this geometry here. Okay. How do you do it? Well, you start with the Coleman-De Luccia instant part. Here it is. What are we calculating? We're calculating fluctuations. Fluctuations about the geometry, fluctuations about scalar fields, whatever fluctuations we want to calculate, we calculate propagators in this or on this Coleman-De Luccia instant. We calculate 2-point functions. Those, we calculate 3-point functions, 4-point functions, any number of them, but let's concentrate on 2-point functions. This could be the 2-point function of some scalar field. It could be the 2-point function of the gravitational fluctuations. Right. Having calculated them in the Euclidean geometry, we can then analytically continue them to the Minkowski geometry. That sounds dreadful, but it can be done. And then we have correlation functions between points up in this region here. Then those points can be extrapolated out to this boundary sigma, and in that way, process of analytic continuation, extrapolation, we can calculate correlation functions. Let's just draw them. I'll draw them as propagators. Correlation functions between points on this boundary. If those correlation functions look like the correlation functions of a conformal field theory, in particular, if there's an energy momentum tensor with the right dimensionality, if it has the right operator product expansion, and so forth, then we might be inclined to suspect that there really is a conformal field theory on here. I'm not going to work out the details. I'm going to tell you.
What's this dimension? What's the geometric interpretation? You said that you're missing a second dimension. Which
Yeah, fine.
What does that mean now?
You what?
Having made that graph? Having made that drawing with that wiggly line?
Right. No, you mean how what are the kinds?
What's the vocabulary?
Okay, the vocabulary has not yet been established. The reason is because we haven't identified the notion of time yet. There are different time slices on here. So,
is it the path parameter?
Is it what?
Is it the path parameter?
No. I'll tell you what it is as we go. It emerges completely naturally, without any effort, and in a surprising way. Okay, so when I say we take a 2-point function, we can take the 2-point function at 2 different times, for example, and then extrapolate to here. Now we have a thing which looks like it's a function of 2 points in 2 times. Okay? What I'm going to tell you is that the right story is a Euclidean quantum field theory with no time direction, but with an emergent time that emerges in roughly the same way, a similar way to the way the interior dimension emerges. That's what seems to happen, and I'll show you how. I'm not sure I'll show you how, because I'm not sure I'll get there. Okay, but let me tell you what the upshot of calculating correlation functions is. In particular, I'm going to focus on the late time correlation functions, not because I can't do more. I can write down the full correlation function, but because of time constraints, I'll focus on what happens at late time. Let me first take the example of a scalar field. Let's call it F. Not the original infraton field, but some minimally coupled scalar field, minimally coupled massless scalar field. The reason I'm interested in minimally coupled massless scalar field is because it's very similar to the gravitational fluctuations. Gravitational fluctuations are typically described by minimally coupled scalar fields. And let's calculate the fluctuation of the two-point function of scalar fields and extrapolate them to this boundary. I'm just going to tell you what you get. You get an infinite series of terms with different time dependencies in front of them, but there is a late time dependence, which is asymptotically the late time dependence, which I'm going to focus on. But actually, I'm going to write the whole thing. It's an infinite sum. I'll write the whole thing. It's an infinite sum over delta. Delta is an integer, and it starts at 2 and goes to infinity. It's called delta because it's connected with dimensions of operators. And then it has e to the delta minus 2 times t1 plus t2. Oh, I didn't tell you what t1, let me write it differently. T1 to the delta minus 2, T2 to the delta minus 2. Okay, what T1 and T2 are they are the two times at which the correlation function was evaluated, T1 and T2. And then there's e to the minus R1, e to the minus R2. R1 and R2 are the radial positions of the 2 points. Radial means distance away from the center. And then there's an angular dependence. 1 minus cosine alpha to the minus delta. Cosine alpha, or alpha, is the angular distance along the sphere. It's the coordinate distance along the sphere. 1 minus cosine alpha to the minus delta is exactly the correlation function that you'd expect in a boundary theory, in a boundary conformal field theory, where the boundary scalar field has dimension delta. If you were doing ADS CFT, where there's an ADS bulk in here, you would discover, oh, I'm sorry, there's a delta here, R1 delta, R2 delta. You would discover that along with the angular dependence, there is also a dependence on radial distance. You usually drop that out. That's something that's associated with anomalous dimensions. And you drop it out of the calculation in comparing boundary things with bulk things. We would do that here too. We just factor it off the same way we do in anti-de Sitter space. And we're left with some time dependence. Time-dependent coefficients times correlators for fields of definite integer dimension. There's one more term in the correlator, and the one more term is extremely interesting.
What about the translation invariance in time?
What's that? The
Time translation. It doesn't seem to be translation invariance.
It's not time, it's not translation, this is cosmology. We have no time translation invariance. But we still have to locate time. Somewhere in this we have to locate time. There are some prefactors here which depend on the time. Now notice, for dimension 2, the time dependence is absent. There's nothing which increases with time. Delta starts at 2 and goes to infinity. So the dominant late time behavior, and just for convenience, I'm going to focus on late time behavior. Late time behavior, these prefactors are not there, and we discover that there's some kind of conformal structure, conformal field, discrete with dimension 2. Now that's a dimension that we should expect for a scalar field if this were anti-de Sitter space. We would normally expect the Lagrange density to be a field of dimension 2. So one does expect a dimension 2 field, and that dimension 2 field is behaving exactly like dimension 2 on the boundary here, is behaving exactly the right way. Then there's another term, and the other term is plus logarithm of 1 minus cosine alpha. Anybody know what that is? Two-dimensional field of logarithms. That's a that's a scalar field, massless scalar field in 2 dimensions. There is apparently underlying or overlying, I don't know how to think about it, overlying the dimension 2 piece, there's a piece with dimension 0. That piece with dimension 0 is simply a dimension 0 scalar field on this surface here. Okay, what's it doing there? Well, I think I'm not going to try to tell you what it's doing there. I'm just going to get on with some properties of this field theory. There seems to be this dimension 2 piece, this dimension 0 piece. That dimension 0 piece tends to constants out at infinity, and it appears to be connected with a degree of freedom which allows you to impose boundary conditions. I'll tell you in another language what it is. It's related to the dimension 2 piece, but it's the non-normalizable mode that goes with the dimension 2 piece. In ABS-CFT, every operator has 2 pieces. One is a normalizable mode. The other is a non-normalizable mode. The non-normalizable mode is always associated with changing boundary conditions in the system. So there apparently is a degree of freedom in the system which corresponds to boundary conditions on the scalar field, just freezing the boundary conditions. But unlike ABS-CFT, there's a probability measure. Given that there's a correlation function for that dimension 0 piece, there seems to be a probability measure for boundary conditions. That's something I find extremely interesting, that part of the conformal field theory and part of the probability measure on that conformal field theory has to do with the non-normalizable modes, which in ordinary ABS-CFT you would identify as frozen boundary conditions that are just arbitrary. Here they're also arbitrary, but there's a probability measure for them. That seems extremely interesting to me because the question of probability measure is at the center of a lot of the difficult questions. Okay, let me now come to the gravitational fluctuations. The gravitational fluctuations are almost very similar. We'll just call them HH. The formulas are practically identical. The formulas are practically identical. In particular, there is a dimension 2 piece. That dimension 2 piece has a correlation function which is exactly right to be a transverse traceless energy momentum tensor on the boundary. So it seems that in calculating gravitational correlators, there does appear to be a energy momentum tensor on the boundary which has the right operator product expansion to define an energy momentum tensor. That's a good thing. And the last thing I'm just going to mention very quickly is that there is another piece in the gravitational correlator which is dimension 0. That means it goes to a constant and doesn't fall off as you go out to infinity. Another way to say it is there's a degree of freedom which corresponds to deformations of the asymptotic geometry. The asymptotic geometry of the 2-sphere, there seems to be an additional field of dimension 0 which does not fall off as you go to the boundary, which if you excite it, would change the shape of the boundary, would change the geometry on the boundary. It corresponds to a Liouville field on the boundary. It is a Liouville field on the boundary. In other words, the boundary geometry itself has fluctuations. This is something that doesn't happen in ABS. In ABS, there is no Liouville field on the boundary. It's frozen. Here, there seems to be a remaining degree of freedom which corresponds to changing the size and shape of the boundary. Well, ask, what does this Liouville field do? This Liouville field is time. And how do you see that it's time? The Liouville field, describing a two-dimensional geometry, is really such that the two-dimensional metric, let's call it G2, the two-dimensional metric, is equal to some boundary metric, let's just call it d omega 2, times e to the Liouville field. And the Liouville field varies as you move around on the sphere. This seems to be there in the correlators, a Liouville field on the boundary. Or another way to say it is there seems to be two-dimensional gravity on the boundary of this system. The two-dimensional gravity is a good thing. And the reason it's a good thing is because the two-dimensional geometry expands with the scale factor. The scale factor determines the overall size of the two-dimensional geometry. It expands with time, but it also expands with the Liouville field. It seems that the Liouville field is the thing which is replacing time in this, and this is a more or less well-known thing to string theorists, that the Liouville field, if it's appropriately defined, can be a stand-in for a time variable. There are two renormalization group flows in the system. One of them is with Liouville field, and it corresponds to the time flow. The other renormalization group flow is the flow that's associated with moving into the bulk. Any Liouville theory always has two flows associated with it. One associated with changing the coordinate mesh, and the other associated with changing the Liouville field. And it seems that, in this case, that the time direction appears to be governed by the Liouville field. Another way to say it is you can remove the time dependencies by decorating the fields with appropriate Liouville dressing and remove the time dependence from these fields, or add time dependence. I'm going to stop.
Is the same statement that the scale factor is like the time?
Yes, it is exactly that. If I had more time, I would explain the connection with the Wheeler-DeWitt equation. Basically, what this is it is a boundary version of a Wheeler-DeWitt equation, which the scale factor, yes, that's exactly right. The scale factor is time. Yeah. Another situation where a very similar kind of thing happens is if you think about Wheeler-DeWitt quantum mechanics, right? You have as your degrees of freedom a scale factor and some field, but you never introduce time. It's just the scale factor becomes time. Here the scale factor is defined on the boundary. This is the scale factor, and it simply grows proportional to time. So that's, yes, it's exactly that connection.
Well, it's very nice if it's adiabatic when you don't have that transition.
At late time, it's adiabatic. And so...
And then it really goes into the Schrodinger equation exactly.
Yes, it goes into the Schrodinger equation exactly. And what that would mean here is a kind of decoupling of the Liouville field from the rest of the system. And it would correspond to a flow to a fixed point. It would correspond to a flow to a fixed point. So let me conclude on that. And the main lesson here is that there is a mathematical structure to be explored, which is the Coleman-De Luccia instanton. And to explore it and to try to see if one can't make a connection with both conformal field theory, anti-de Sitter space, and to find a precise string theoretic description of this geometry. A precise description of the geometry would, in a sense, entail a classification of both the things that you can tunnel from and the things that you can tunnel to. Okay, I'm finished, and I'll take any questions now if anybody has any.
How about you getting out of a mini superspace and getting a local?
Oh no, this is not mini superspace. This L here depends on an angle.
What I meant is relating local time to the gravitational field.
Well,
here you're relating global time, a cosmological time.
Well, L is a function of position on the two-sphere.
So it is.
It's local, but it's on the
So
two-sphere.
it is.
Right. So what I'm speculating is that there's a Wheeler-DeWitt formulation, but all of the degrees of freedom are on the boundary.
Look,
But all the degrees of freedom are on the boundary. A hybrid between holographic things and Wheeler-DeWitt. That's what this seems to be. But as for now, there is, I think, substantial amount of evidence that there really does exist a conformal field theory on here, which what to do with it, who knows? Okay. Yes.
Have you tried to calculate the central charge?
Yes. Yes, the central charge is interesting. The central charge is the entropy of the parent de Sitter space. Now that sounds small, okay? So you might ask, is that enough degrees of freedom to describe this gigantic growing universe? The answer is that the connection between central charge and number of degrees of freedom is a little bit different than a Liouville theory. The usual thing is that the central charge is proportional to the number of degrees of freedom times the coordinate area of a region. The number of degrees of freedom is the central charge times the coordinate but coordinate area. But with Liouville, there's another factor here, which is e to the twice the Liouville field, which turns it into proper area. Okay? If the Liouville field is increasing as a function of time, e to the Liouville field, then this simply translates into the physical area times the central charge. And so the number of degrees of freedom at any time is, in fact, proportional to the area of the sphere in Planck units. But the area grows through this factor, not through the coordinate area. So the central charge here is equal to the entropy of the background de Sitter space that you decayed from. So it can be small.
that's beautiful, Lenny.
Yeah, well, we'll see where it goes. Well, all right.
It's written up.
Nobody's exhausted. Yeah, it's written up. It's written up. I haven't had much time to do very much about it because I've been writing books, but I'm finished writing books.
But it is written.
It's more than a year old, but let me tell you one more very interesting little part of this story, which I find extremely interesting. It has to do, well, on one hand, it has to do with this difference between parallel and series description of things. On the other hand, it has to do with bubble nucleation and bubble collisions. Let's come back to this picture. I've pretended that it is meaningful and sensible to have a single bubble disconnected from other bubbles. There might be another bubble over here, but I've imagined that the bubble that I'm interested in is an isolated, completely isolated thing with no other bubbles immediately adjacent to it. Now that's quite impossible. The reason it's impossible was pointed out, first of all, many, many years ago by Guth and Eric Weinberg. And to say it simply, just draw a line, a time-like line that goes right to this point sigma. Goes right to sigma there. Now that time-like line is infinite in duration because the metric diverges up near this point here. If it's infinite in duration, and there is a finite bubble nucleation per unit time along that line, then you can bet there will be another bubble nucleation along there. And so another bubble nucleates along there. And will inevitably collide with our bubble. That can't be avoided. Well, if this one, same thing over here, same thing over here. What Guth and Weinberg point out is not that you'll have isolated, pristine bubble, Coleman-De Luccia bubbles. but that you have isolated islands of bubbles, isolated islands of infinitely many colliding bubbles. Now, the colliding bubbles are kind of interesting. The question is, what might they mean in a conformal or in a boundary field theory? So let me try to give you some picture of what supposing a bubble collided, and let's let this bubble, just for fun, let's let it have a non-zero cosmological constant inside it. So here's a non-zero cosmological constant, and this is just for fun, I'm just exploring this possibility. It collides with a world which has no cosmological constant. There's got to be a domain wall in between. So a domain wall separates these two things. And since this has a positive cosmological constant, it will have to end off with a space-like boundary. It will look something like this. Okay, this is a domain, this is a bubble which formed at a relatively early time. Let me draw another one over here, which happens at a very late time. It's very small by comparison. It looks extremely small. And now let's look at the boundary sigma. Let me draw the boundary sigma for you now. The boundary sigma goes like this. It intersects this point here, and it intersects this point here. And you simply think of it, take all the backward like lines from t equals infinity, and just terminate them when they intersect some de Sitter space, when they intersect something different than empty cosmological constant 0. Intersects over here. Now, as we sweep around on this green line, we will go from places where we intersect pink bubble. Let's give the background geometry, the original background geometry, let's make it blue. Here's blue. As we sweep around, we will go from some places where the boundary here intersects pink stuff, and then intersects blue stuff. And then comes back over here and intersects some pink stuff. What you would see on the boundary surface sigma, the boundary surface sigma would look like this thing. It would look mostly blue. Now by mostly blue, I mean it would be adjacent, contiguous with the de Sitter space of the blue kind. But then there would be a little scar over here, a scar of this collision over here, which would look pink, a little circle. And another little tiny one over here, because it occurred later, over here. What are these things? How do you interpret them in the conformal field theory? They look to me very much like, well, first of all, they're non-perturbative things. They're non-perturbative. Each bubble nucleation costs you an exponential cost. So they're non-perturbative things from the bulk point of view. I think they're also non-perturbative things from the boundary field theory point of view. I suspect they're just instantons. There's some form of instanton in an unknown field theory, which, well, they're by definition instantons. They're localized configurations. They're localized configurations, non-perturbative in origin, exponentially suppressed. And in a conformal field theory, they have to exist at every size scale. They have to exist large ones, they have to exist small ones. The small ones correspond to bubbles which nucleate at a very late time, very close to here. The large ones correspond to bubble nucleations at earlier times. If you look back from a late time, you'll miss the small ones, but you might see the big ones. This is part of the infrared ultraviolet idea. Things which are very late in time, or which can be seen from very late in time, in other words, very infrared, appear in the conformal field theory as very small scale structure. That's the pattern. That's a pattern here. That things seen from very, very late times will include small distance structure on here. Things seen from earlier times here will only see larger scale structures. So there's a natural notion of infrared ultraviolet connection that needs to be explored. This is late time in two senses. It occurred later than this as a bubble nucleation, but it can't be seen from the interior here until a later time. So as I say, there's at least one notion of infrared ultraviolet mixing, or whatever the right word is. Yeah, so the point I was getting at is that potentially any one of these conformal field theories could know about a lot more than just one vacuum that you begin with and one vacuum that you end with. It may have all sorts of structure in it associated with instantons, big ones and small ones, which may know about many other vacuums. Now, this is speculative. I'm getting to the point where the speculations are getting out of control and all stuff.